Welcome to the massive open online course on computer science, the subject operating systems, the topic system calls. The textbook prescribed deals with the following topics in the chapter which has the content for this particular topic system calls: operating system services, user operating system interface, system calls, types of system calls, systems programs, operating system design and implementation, operating system structure, virtual machines, operating system debugging, operating system generation, system boot. Each of these topics is very vast subtopics in this chapter. It is a condensed version of so many important topics in operating systems. Therefore, what I wish to do is to quickly start with the last topic, system boot, and then move towards understanding the idea of system calls, types of system calls, system programs. The essence of this exercise is that in the beginning the machine is completely switched off. The moment the machine, the hardware machine is switched on, there is a power on self test which is performed by the hardware. It is called post power on self test. The simple check which the machine does enables us to understand whether all the critical components, critical chips, critical boards are working the moment the power is on. We of course take care of the fact that there is no spike, there is no reason to believe that the power supply is so erratic that it will spoil some of the chips. The chips are sensitive. Today the machines are very rugged, they can work anywhere. However, for quite a long time the entire environment was air conditioned and the dust freeness of the environment must be ensured. But however, over the last 25 years we have seen the machines becoming more and more rugged. We can use them anywhere. Today a mobile has much more computing power than a machine that was there 20 years back. The mobile does not need any specific air conditioned environment or a dust free operating conditions. We work, we use the mobile, we are careful. The machines not only grew in ruggedness but also became very miniature. Even the best of the mobiles, the most sophisticated mobiles, is just pocket sized. Today we are talking about palm tops. Whatever be the size and the shape of the machine, the computing or communicating machine, what we need to understand is the moment it is switched on. Today we are talking about mobiles where we never switch off. The mobile is always on, 24/7 it is on. So, the ruggedness of the system is not only in sustaining or withstanding the varied environments, the physical operating environments, but also the operating conditions. 24/7 the machines are on, the servers are never switched off. Only for maintenance, occasionally once in a week, once in a fortnight, we have a routine shutdown of the machines and then reboot for about half an hour or 40 minutes, all services will be suspended. However, we need to be very careful to note that whenever the machine is switched off and it is brought back to switch on condition, there will be a power on self test which tells us that these are the chips that are activated, things are up and running. And if any of the chips is fallen sick or not responding, it is always better to seek for a safe shutdown rather than think that it will come out after next 2 minutes, next 3 minutes will be alright, and then go ahead and create havoc for many users. So, we have been talking about ruggedness, fail safe systems, we need a power on self test, we need 24/7 operations. The concerns are many in terms of reliability, dependability, and these are all becoming very serious, and therefore the system booting process, which begins with power on self test, automatically thinks of where to locate the operating system. It is there in the secondary memory. It has to fetch the boot record of the operating system into the main memory and then activate automatically the boot record of the typical operating system, it can be any operating system, will bring in either the kernel in the case of Unix or the internal commands in the case of MS-DOS. Certain commands will come into the main memory and the operating system says yes, now it is up and running, and there are plenty of operating system services. We should never forget the fact that the operating system itself is an excellent piece of software with lot of interface to the hardware. The hardware gradually gets shielded from the user. The user looks at the operating system, whatever many users, many tasks want to do, the operating system steps in between the machine and all these users and tasks, make sure that the system is being used efficiently, the return on investment on the costliest component, that is CPU, is maximized by the utilization, there is minimum waiting time, very quick response time, we have a very good throughput. Overall, all users are satisfied. Towards this end, after the operating system is booted, we need to talk about an operating system generation, where the concerned program segments of the operating system are coming into the main memory. There was a point in time, as I mentioned in an earlier topic, the entire main memory size was only 640 kilobytes, and we were thinking that's a big size of main memory. A little bit of that main memory can be spared for the resident monitor, namely the operating system's original way of getting into the entire main memory. The resident monitor was a very sleek work done by the designers, and it takes care of some minimum I/O support. But today the operating system has grown in size, it is expected to offer more services. The users have become more and more consumerist. They are not aware, they are not, neither are they interested in studying the entire hardware, what is the quality of the hardware, what is this power on self test, where is the boot record. Everything is expected to be taken care by the operating system. We just plug the machine in, switch it on, and automatically everything that I want to do must happen. The users are more focused on their task. They want to do multitasking. Multiple users are sharing the resources. The network is the computer. Your machine is no more in isolation. And we are talking about so many things, 20 to 25 functionalities of an operating system are today nicely identified, and the operating system generation soon after the boot record is fetched is taken care in a manner where within the available memory for the operating system, the core functionalities are shipped. By design, the Unix is structured as a kernel, the kernel comes in and all others are fetched back by the kernel. Once the operating system takes charge of your machine, all resources, we go through only the operating system. These functionalities are good for the designer. We need a memory manager, we need a CPU scheduler, we need a file manager, we need an I/O device manager. All these ideas are functionalities. These functionalities are for the person who is developing the operating system. There are conflicting demands, there are serious constraints. Amidst all these constraints, the designer has implemented a policy and a mechanism. The functionalities of different operating system may look similar, but then the way they get implemented based on the hardware, the choices made by the designer is completely different. We have multiple operating systems. So operating system generation is actually to find out what to get in. Say for example, in the DOS world we have internal commands, external commands. When the external command is called, the internal commands are overlaid. We created an overlay file, otherwise MS-DOS itself becomes very bulky. It occupies the main memory, throwing out all user programs, very limited space for the user programs. Not all users require all the commands. Every operating system is a host of commands. It's a big exercise. Typical users use about 3 to 4% of what the operating system functionality can support. Even application programmers are not able to go any beyond 7 to 8% of what the entire operating system does. Therefore, we do not need the entire operating system code to work with. It is there, it is managing the hardware, it is giving you the feeling that once the machine is on and the prompt comes, login prompt comes, you are up and running with your own work. There is nothing else in your mind, exactly your work is being carried out. but then to make it happen there are so many functionalities. However, we know that the piece of software that has become operating system is an excellently written code. There is a lot of code that can be used by the application programmers to make the application program faster, to make the application program writing happen in a quick time. We can reuse the code. So, certain things from the functionalities, different functionalities of a given operating system are nicely packaged as operating system services. We have operating system services, we have a typical system interface, system calls, types of system calls, we have systems programs identified in each functionality which can serve as extension of your application program. You can just get appended kind of a thing to the application program and it runs through the application program. Therefore, we have been talking about a clever design of the operating system and its implementation. The policies must be clear, there are many constraints, conflicting demands, very limited resources. To some extent, the ideas of grid computing and cloud computing have given us an idea that all resources will be unlimited. You just tell how much of each resource you want, we will get it from somewhere. It is just the case of picking up the kind of a resource that you want, talking terms, talking about service level agreements, and yes, we have done it. You got your resource wherever it is. Why are you bothered where the resource is? You want this resource, this is the implication of that. Operating system structures, different operating systems have been structured differently. We talk about kernel structure, we talk about layered structures, we talk about overlay files, we talk about Windows NT new technology structure. After Java has taken off, we had virtual machines. The idea of virtual machines is so central to implementing cloud computing. It is so central to understand that a virtual machine is a little bit of hardware abstraction, a little bit of application binary interface, and a little bit of application programming interface. Virtual machine as an idea is nothing new. It was there in the late 70s. After 35 years, we found a great application for virtual machines. Today, most cloud computing platforms talk about virtual machines. The language level implementation of a virtual machine has happened in Java, which is a runaway success. There are reports that keep telling that today Java is also a legacy language. It is an old language with a lot of features. Debates can go on everything. We can create a debate. It is healthy debates which we encourage, and we do not want to be conclusive because there is nothing like one technology will kill another technology. We need to be matured enough to understand where to use the technology appropriately, how to get the maximum out of the technology based on what the designers have thought it is a good policy and what the implementation makes it available to us. Therefore, there are conditions where in this exercise the operating system may crash. What do we do with that? The system, as I said, fail-safe systems at the time of power on self-test, if one of the chips is not responding properly, it is better to shut down. Safe booting. We talked about so many things. There is a risk in it: default booting, full system booting, safe booting, error booting. All these things are now different conditions which we understand. Most of us do that. Mobile phones, the operating system also crashes. How do we bring it up? What happened to the data? That is the concern. It does not matter to me if the entire system, mobile system crashes. Once it is repaired, am I going to get back all my data? Is my address book intact? Has something gone? I have stored lot of messages. These days I am not even taking backup. I am presuming that somewhere it will be stored. Suddenly I get one message saying that it's all memory overflow. There is no memory. Serious problem is existing. You have to clean up, you have to purge. Until then I am using the memory. What happened to that data? All these concerns are there. Therefore, we go back to this idea saying that there must be some operating system services. When the operating system is running, up and going, we need to use these operating system services effectively to get our work done. So, what are those services? To describe the services an operating system provides to users, processes and other systems, to discuss the various ways of structuring an operating system, to explain how operating systems are installed and customized and how they boot. All this is described. Operating systems provide an environment for execution of programs and services to programs and users. One set of operating system services provides functions that are helpful to the user interface. How do I interact with the operating system? Command line, graphics user interface, batch processing. The very good old systems, what they were doing is creating a facility for batch processing, which is what is called combine all C programs one after one user C program, another user C program, load the compiler once, start the execution of the batch of C programs. It worked. Batch processing systems were some of the very early systems. Gradually this idea of batch processing gave away. Today we talk about job sequencing, job scheduling. It blossomed into a fantastic functionality of operating systems called CPU scheduling. Now this batch and the way we were interfacing with that machine used to occupy a very big floor, and all that we know was take the punched cards, keep one after the other. There will be a computer operator who will make sure that the bunch of cards will go. What happens if one card is found faulty, the machine is not recognizing? You have to throw away the entire batch and then take it up afresh. All these concerns were there. It's a very rudimentary, batch processing is a very rudimentary interface. Then we moved to command line interfaces. Then we started graphics user interfaces, which is windows, icons, menus and pointers. So three varieties of interfaces we have seen, and of which the most popular is the GUIs, graphical user interfaces. Today wherever we go, we talk about windows, icons, menus and pointers. Program execution time, when the program is executing, the system must be able to load a program into the memory and to run that program and execution either normally or abnormally. Abnormally is an error condition. What happens if a user program ended up in an error? Different operating systems deal with it differently. In Unix, it is simply dumped into the shell of the user, which we will talk later, which is a later topic which we will understand that. I/O operations, a running program may require I/O which may involve a file or an I/O device. How do I know whether the file is available? What to do if the file is not available? How do I signal to the application program or user that the file is not available? How do I keep it as an open file? How do I tell how to close the file? All these things are simple services. I need not know about the functionality called file management, whether it is in the secondary storage, whether it is sequential access method or indexed sequential access method or a hierarchical indexed sequential access method, or is it an NTFS, new technology file system made for Windows NT, or is it simply the good old Unix file system? I need not know anything about it. The functionality is a file management, but the services are manifested as opening a file, closing a file, doing certain specific operations with a file. Similar is the case with I/O device. Today I do not have to worry about where the device driver is to recognize this device. I will simply plug that device, and over the net I will search for a device driver which recognizes this device and acts on it. File system manipulation. The file system is of particular interest because everything we do is file. The file system is of particular interest. Programs need to read and write files, directories, create and delete them, search them, list file information, permission management. These are the services. They manifest very nicely as services on I/Os related to I/O devices and the files. Files and I/O devices are very important for the user, and we provide certain operating system services. They need not do a formal course on operating systems internals to find out how the file management functionality is implemented, how the device management functionality is implemented. It is true that there are levels of courses in a typical academic coursework. We talk about simple operating systems, we talk about advanced operating systems, we also talk about operating systems internals. We normally categorize study of the functionalities and the way they are physically taken to implementation and the policies are made as internals. we need not study the operating system internals. I need not know precisely what is the operating system configuration, what is the hardware configuration. I have come here to do this lecture, it is facilitated. I know how to switch on this box, I know how to launch my PowerPoint presentation, I know which directory the entire PowerPoint presentation is there. I must definitely have the support from the administration. My colleagues here make sure it is like that. I can simply come, switch on, go ahead and use the resources. I need not know how much of the operating system is working now. Is it 3%, 5%, 7%? My job is done. My task is taken care. That is why they are all manifesting to me as services of an operating system. The functionalities are more in depth, they occupy more time, space, everything. It is a study of the internals of the operating system, which is for a completely different purpose. I am a user here and I know how to use these services to make things happen. At the communication level, there are certain nice services. We do not want any computer to operate in isolation. It is always over a network, and the communications may be via shared memory or through messaging, and it nicely interacts with the ISO OSI protocol. All those physical layer, media access control, data link layer, network layer, transport layer, session layer, presentation layer, and the application layer, peer-to-peer communication. There must be lot of support from within the operating system, but as far as I am concerned, an application program called email package is launched by me. I launched it, I logged into my email, and I am only sending the messages, receiving them, managing my mailbox. The rest of the story is taken care by the operating system and the internals. If something goes wrong, we will see what it is. Error detection. OS needs to be constantly aware of the possible errors, may occur in the CPU, memory, it can occur anywhere. Debugging facilities must be there. It is very difficult. If there is a deep rooted error, and the operating system will have to be aborted, completely cleaned up, reinstalled, rebooted. It can also happen. Occasionally we run into those conditions, but earlier on it was a very common place. Operating system will get corrupted, you better shut down and then reboot. Corrupting of the operating system can happen. There are so many things which are out of control. Viruses are there, worms are there, security lapses are there, protection lapses are there. It is always better when in serious doubt about the operating system, instead of impacting lot of people adversely, shut down. Even if it takes half an hour to 40 minutes, reboot the system, reinstall the operating system, take care of going ahead as though we have just parried over. These are called fail safe operating system procedures. We do not mind shutting it down and restarting, rather than thinking, presuming that everything will be set right after some time, and then go ahead and destroy so many other users' works and tasks. It can happen, can potentially happen. And today what is happening, the users are not willing to accept this method of shutdown. Even if for 1 minute the system is not there, they are telling, how can I survive without a system? Half a minute the system goes, the problem is there. So these are certain changes which technology absorption into the society at a pace which we did not expect has brought in. They cannot think of shutting down their mobile phone even for 1 minute. Always 24/7, we expect that it is up there. Whether I use it or not is secondary. Simply on, it is there. I am also sleeping, the mobile is also sleeping. It is just there. There are so many other services, resource allocation, accounting, how to keep track of it, protection and security, which are good topics. Essentially, this is a set of services which are nicely provided to the user by any given typical operating system. How it is structured internally, that is a separate study, but this many services are there. User and other systems programs, we talk about all of them out here, and what we are doing is to note that the GUI, batch, command line, user interfaces level, program execution level, IO operation level, file systems, communication, resource allocation, typically for a given operating system, for a given computing environment, this many areas are necessary to make the users feel that the operating system is reasonably good, generic, it is allowing them to take care of all activities, and consequently the services are manifested like this for the user who works through the user interface, takes care of the system calls, and these are the services which we want to access. The operating system's functionalities are very deep, they are more oriented towards the hardware. They would work, operating system works with hardware, all efficient use of CPU, efficient the minimum waiting time, maximize response time, all those are very nicely taken care by the operating system. For the user, in this many areas the operating system will provide services. If you know how to take advantage of those services through the system calls, you can use the typical user interface and use it. In summary, an excellently written code which belongs to the operating system is now available for every user through a system call, through a user interface. They can write it in the application program, it will be very efficient. We do not have to reinvent the wheel, and it can happen very nicely, seamlessly. A typical structure, the Unix operating system structure, as I was mentioning, the kernel is here, and what we need to therefore look at is the entire system call interface to the kernel. Now, the kernel here is non-preemptive, that is, you cannot halt the processing of a kernel for any reason. If it is already assigned to do a work, it will complete the work and get back to the next work. For any reason, the existing work being done, existing execution being done by the kernel is not going to be halted. It will complete and then come. So, kernel interface to the hardware, as I said, the Unix operating system is structured like this. It has a kernel. Once the kernel is brought into the main memory at the time of booting, everything else falls in place. The kernel knows how to locate everything else, and it takes care of your requirements. I need not, in theory, as a user, know what is this kernel, where it is, how it is functioning. I have switched on the machine, it asked me for a login prompt, I gave my correct user ID, I gave my password, and everything is running. This is what I want to do, and this is how I wish to work. User operating system command line interface, this we are aware of it. It's a very rudimentary way, the commands are very cryptic. GUI has good windows, icons, menus and pointers. Some operating systems provide both command line interface and GUI. We have different names for it: Apple Mac OS, Solaris, Java desktop, KDE, K desktop environment, Java has a desktop. The GUIs interfaces have improved a lot. Now, you look at this, the command line interpreter, the sample, see how cryptic it is. You yourself will not know what exactly you have been doing. It is very difficult to know that this is the way in which we have been working. The command line interface is very cryptic, we do not know where the prompt is. So, this is how we have been talking about all those ideas which have come about, and what we want to do is to make the interface look very clean. See, GUI interface is nicely segregating your work. System calls are there for the application program. API is application programming interface. We also have mostly accessed by programs via a high level application. We do not want the direct access to the system code. We wish that we work through an API. API will give you a nicer interface to the operating system, shields the application from any damage. If the operating system crashes, your program will not get damaged a lot. System calls are a good interface, but we want the system calls to be available through APIs rather than system calls. The system also can crash. So, we talked about example system calls, standard APIs, system call implementations can be many through the API. This is the summary of it: user application, system call interface, it goes into the kernel mode. Once it goes into the kernel mode, we will not preempt, the operating system will take care, and that is how we work. We do not want to have a direct access to system call. Where possible, we want to use application programming interfaces. The standard C library will give you application program, you can pass parameters, it just becomes a function. API level is just a function that is belonging to the operating system. System call level is a direct interaction with the software of the operating system, that is a little more risky. This many system calls are there, you can keep using it. File management level device management level, information maintenance, communication. This is a wide range of system calls for Windows and Unix calls. So, I have mentioned that for many functionalities there is a provision for system calls and APIs. That is the topic today. Thank you.